Hello, in this video we're going to maximize output subject to a cost constraint. We're going to use a Lagrangian technique and a CES production function. A firm wants to maximize output subject to spending $1,000 on production. The wage is $10 and the price of capital is $2. Output is produced according to the following CES production function. First thing we'll do is form the total cost equation. $1,000 is how much we have to spend on production. T is the wage, 10 is the wage multiplied by L, and 2 is the price of capital multiplied by K units of capital. Setting up the Lagrangian, we're trying to maximize output. Okay, the output is given by this production function, subject to the constraint of $1,000 minus 10L minus 2K. I'm just moving this 10L to the left-hand side and 2K to the left-hand side. So that's why they appear as minus signs in front of the 10L and 2K. We will take the partial derivative of the Lagrangian with respect to L units of labor. So we're going to take this 2 and bring it down in front. So I do that. And then 2 minus 1 just leaves us with 1 or nothing here. And then inside the parentheses here, we're going to take the derivative of what's inside parentheses with respect to L. And so the derivative or partial derivative of L raised to the 0.5 is this last result here. Bring down the 0.5 in front of the L. 0.5 minus 1 leaves us with minus 0.5. Then we have to be aware of lambda is being multiplied by minus 10L, and the derivative of minus 10L lambda is just minus 10. We don't have to worry about lambda times 1,000 or lambda times minus 2K. No L appears in those terms, and so therefore we treat it as a constant and drops out as a 0 when we take the partial derivative. We'll set the Lagrangian equal to 0. We'll do a similar thing, but this time a partial derivative of the Lagrangian with respect to capital. Very similar partial derivative, bring the 2 down in front, 2 minus 1, we just have 1 here, and then looking inside parentheses, the partial derivative of k raised to the 0.5 is this result here. Need to be mindful that lambda is being multiplied by minus 2k, so the partial derivative of minus 2 times lambda times k is just minus 2 lambda, setting that equal to 0 then. And then taking the Lagrangian and taking the partial derivative of it with respect to lambda, we get back the constraint. The next step is I'll take these first 2 partial derivative results from the last screen, and I'm going to solve each equation for lambda. So solve each equation for lambda. I'll start with this one up here. Moving this minus 10 lambda over to the other side, we have this result. Dividing through by 10, so 2 divided by 10 is 1/5. Everything else here is unchanged. And then we're going to look now at the other partial derivative. We're going to take this equation and we're going to solve for lambda. So the first thing I do is this minus 2 lambda, I move over to the right-hand side. And then I'm going to divide through by 2, and we get another expression for lambda. We're going to take these 2 lambda equations and set them equal to one another to get rid of the lambda. So here's our lambda equations from the last slide. Setting both equations equal to each other, lambda equals lambda. We have this result here. I'll note that what's in parentheses here, this k to the 0.5 plus L to the 0.5 appears on the right-hand side, so that just cancels when we divide through, leaving us with this step. The 0.5s will also cancel now in the next step. I just multiplied through by 5. That's where the 5 is now over here. And then we're going to raise both sides to the minus 2 power. So L to the minus 0.5 times, or raised to the minus 2 is just L. Same thing with k to the minus 0.5 raised to the minus 2 is just k. And then 5 raised to the minus 2 power is actually 1 over 25. So we have a key result here, and we're going to use this result and plug it into the cost constraint. So from the last screen we had this. We're going to plug that into the cost constraint. So where I have L, I'm going to plug in K divided by 25. And now simplifying, we got 2.4K on the right-hand side, and we'll see that K equals 416.67. That's how many units of capital we would hire. And to get the units of labor, we'll just take this 416.67 and plug it into this equation up here, and we'll use 16.67 units of labor. So that is our optimal input mix. That'll give us the maximum output for spending $1,000 on capital and labor. Okay, I hope you found this video helpful.